Hi, and welcome to Chapter 11. In Chapter 11, we're going to be covering subnetting, which will be breaking down your network into multiple subnets using your IP4 address. Let's get started. As you can see from our roadmap, we're getting to the second half of our book, which is great. Chapter 11 is definitely past the halfway point. And you can see we're going to do addressing and transmission. Hopefully you got through TCP/IP last time just fine. We'll do subnetting and then add some more transmission information. Then we'll start talking about some other access and administration of your servers. One of the most important things you need to learn when it comes to subnetting is the base 2 binary system. This can be a little difficult for some people to understand or visualize because we've always worked in base 10. 0 through 9, and then you roll over to base 10, 10 through 99, and we roll over to base or to 100. So base 10 is what most of us think of when we think of numbering. In digital electronics, we use binary or base 2. So we start with 1, and then every time we get up to a base 2, we roll it over. So 1, and then 1, 0 would be 2, 1, 1 would be 3, 1, 0, 0 would be 4, 1, 0, 1 would be 5, and so on and so forth. Understanding where the positioning is. If we were to look at this on a decimal system, we would be looking at our 1, 10s, hundreds, thousands, 10,000s, 100,000s in our periods in regular decimal system. In binary, they go powers of 2. So 1, 2, 4, 8, 16, 32, 128, 64, 128, 256, 512, so on and so forth. So understanding your base 2s is going to help you to understand this and recognizing that these are the numbers. You're going to want to memorize these. If you don't already have them memorized, you are going to want to memorize your base 2s all the way up to 1024, I would say. But the reason why is because when we do subnetting, you're going to be using your positions in a binary octet or 8 numbers, which is why we only go up to 128. So an octet, 8 binary numbers, will get you up to 255 possible. So all ones, 8 ones in a binary system is 255. If we take 128 plus 64 plus 32, 16, 18, 4, 2, 1, you will get 255. Binary system. Understanding how you can get to that number is going to help you to visualize when you see a decimal notation of a binary number, say 149. Remember, we go from 0 to 255. 149. What is 149 as a binary? So in this case, it's 100100101. And you can see that's 128 plus 16 plus 4 plus 1, because each one of those positions adds in its number. If you have a 0, it doesn't add that number. So we don't add 64, 32, 8, or 2. Those don't come in. We add all of our numbers up to get to our decimal notation. Being able to convert from decimal to binary, from binary back to decimal, is really going to help you when we get into subnetting, because we're going to be dealing with octets of binary numbers and understanding when we borrow bits how that works. As you've seen before, we use a dotted decimal notation when we identify our IPv4. So we're always talking about IPv4 in this chapter, in our IP address. Dotted decimal notation describes each octet, 8 bits of the IP address separated by periods. An octet, 1111, 1111, so 8 ones, can get up to 255. Every time you see all ones for 8 binary numbers, you know it's 255. So in the situation we have here, our IP address, 130.50.125.25, is listed out in binary, and being able to understand how to convert from one back to the other is going to be important. When we look at our IP address, we next look at our subnet mask to figure out which portion is our network and which portion is our host. In this situation, we have a class B address. The first 2 octets are our network, the second 2 octets are our host. So in this situation, 130.50 is our network, and 125.25 is our host, because we separate those out. Looking at them in binary will help you just kind of visualize that 255, 255, and then the 00, because the purpose of a subnet mask is to tell you what is my network section. That's an important thing to remember. So in case you missed that last chapter, the subnet mask tells you which point is our network section, not our host. We are not dealing with our host with our subnet mask. We want to know what the network is. And we do what we call a bitwise AND. We take the binary notation of the IP address and we AND it with the subnet mask. So all of the ones are going to get those numbers coming out and all of the zeros will not. So we do this on purpose so that we can AND really quick. Mathematics, electronics uses binary ones and zeros to understand everything. And the more comfortable you get with binary and bitwise ANDs and so on and so forth, it's going to make it easier. So we use this dotted decimal notation. You have to remember the term dotted decimal notation to refer to this dots or periods in between our decimal notation of our octets. So now what is subnetting? Okay, as we described a couple of slides ago, the subnet mask splits your IP address into network and host. Part of it is the network, part of it is the host. Our standard subnetting bases it on class A, B, and C. You can take the first 8 bits to be class A, second 8 bits class B, for all first 3 octets to be class C. And then do that bitwise AND to be able to find your network versus your node. Okay, that's standard subnetting. Subnetting in general is going to allow you to extend your subnet mask to use bits from the next octet over. So the easy way to subnet, break it down into A, B, and C. A, B, and C allows you to have a certain number of possible nodes and go on with your life. However, sometimes we don't want to do it that way. We need to subnet. We need to break up our network into different subnets inside of our network. Subnet, network, network, subnetwork. So when we do subnetting, we extend our subnet mask and borrow bits from the node address octet that's next to it. In the example here, we have a class B subnet mask of 255.255.0.0. We are going to extend that class C subnet mask to take 2 bits, singular bits, from our host address. So we have our 255, and then 1, so 2 bits from the left-hand side of our octet of our host. Well, I'm sorry, 3. This one uses 3. So in this case, we're going to borrow 3 bits. 1 with 5 zeros is 224 when you look at it as an octet. You have to look at the whole octet together. And we've only borrowed those first 3 bits. So those first 3 bits gives us 111000000, which is 128 plus 64 plus 32, which gives us 224. So the decimal notation for our network subnet mask now is going to be 255.255.224.0. So that's our extended subnet mask. You can see how we've taken that binary and put it into our new subnet mask. By doing this, we give ourselves those 3 bits that hang out in our host section. We're now going to shrink our host section so that it's only 8 bits and then 5 bits. So that's the host. And then the network is now going to be 8 bits, 8 bits, and 3 bits. Those 3 bits that we borrowed can break down into 8 possible binary patterns. Recognizing binary patterns comes in important here. When you look at binary patterns, we start with all zeros. Remember, we just did this. All zeros is 0. All zeros with a 1. So 001 is 1. 010 is 2. 011 is 3. So on and so forth. 100 is 4. 101 is 5. 110 is 6. And 111 is 7. 0 based, starting from 0, going up to 7, gives us 8 possible binary patterns. We have now subnetted our base class to produce 8 possible binary patterns. Now, in your new binary patterns, the 0 and the 7, so in this case, the top and the bottom, the zeros, all zeros, and the all ones, no matter how many binary bits you borrow, all zeros and the all ones are going to be reserved. We're going to talk about what they're reserved for in a minute, but those are going to be reserved, and you can't use those two positions to make your new subnets. So 0 and 7 are reserved. We had a possible of 8. So 1 through 6 are allowed to be new networks, new subnets that we can use. So we have 6 possible subnets that we can use, because you can't use all 8 because the first and the last have to be reserved. So you could have 6 in the middle. If we had done this by extending it to 4 bits or to 2 bits, same thing. First and the last have to be reserved, and you have however many possible values exist inside of that. So if we had only borrowed 2 bits, we would have had 0, 0, 0, 1, 1, 0, 1, 1. We would have had 4 possible binary options. First and last are used, which means you can only make 2 subnets at that point. We're going to cover a little bit more on how to do this as we go along. Couple of things to memorize, and depending on how you feel about binary, this may be intimidating and it may be really, really easy. First off, what are the possible, I'm actually going to start over on the right, the binary decimal patterns. How do you convert from a binary number to a decimal? By following a pattern of increased bits. So starting with 1 bit, if we just have 1 bit and all zeros, 1 bit over on the left-hand side, that's going to be 128. And you can see that. As you go down, 128 plus 64 is 192. 108 plus 64 plus 32 is 224. 240, 248, 252, 254, and 255. These are our possible binary to decimal patterns when we're borrowing bits from that host node. So if we borrowed 1 bit, we would get 128. If we borrowed 2 bits, it would be 192, so on and so forth. And then we just did the 224 with borrowing 3 bits. So those are the basic binary to decimal patterns, and trying to remember those numbers, memorizing them, understanding 1, 2, 3 is going to give me 128, 192, 224 is going to help you. Worst case, if you don't memorize them, you can add them up as long as you memorize the 128, 64, 32, 16, 8, 4, 2, 1. As long as you get those memorized, you can add this up manually. But if you can memorize the 128, 192, the added up value, that's going to help you. For Class B addresses, starting with 255, 255.00, that's a base Class B, okay? And there are no subnets in that. This gives you how many hosts, how many subnets can you have at each one of those number of bits that you borrowed. So when we borrow 2 bits, I don't know why they don't have 1 on there, but when we borrow 2 bits, we have 255, 255, 192. Okay, so you take out first 2 bits, 128, 64, you get 192. That'll create 2 subnets. Oh, I know why, because it doesn't create enough subnets. So that'll be 2 subnets, and it can hold 16,000 hosts per subnet. So each subnet now has a possibility of 16,000 hosts. As we go down, number of bits 3, so that 224, now we have 6 subnets. Remember, we talked about that last slide. And there are 8190 possible hosts. We've subtracted out the top and the bottom. It would have been 8192, but it's 8190 because we took out that top and the bottom, the zeros and all ones. Keep going down and you'll see up to a base Class C, which is the number of bits borrowed, it's 8. We took all 8 bits from our third octet, so it looks like a Class C subnet mask. But in this case, we created 254 subnets with 254 hosts each. Then we can keep going down. You can continue this if you have a Class B address all the way down to borrowing 14 bits out of the 16 bits that you have in your third and fourth octets. If we chose to borrow 14 bits out of the 16 bits, we could create 16,000 different subnets, but each subnet only gets 2 hosts. So you can only have 2 computers or 2 devices per subnet if you were to go down that far. The smaller little graph at the bottom on the right-hand side shows you Class C addresses borrowing bits. So if we started with 255, 255, 255.0, start by borrowing 2 bits. 2 bits would give you 2 subnets, same way it did by borrowing 2 bits with Class B, but each one of those hosts is 62. Same with number of bits borrowed is 3, 4, 5, and 6. Once you get up to borrowing 6 out of the 8, you end up in that same bottom position. You have 62 possible subnets, but only 2 hosts for each if you had a Class C address to start with. Memorizing these, again, is going to help you to recognize. You may not memorize how many exact hosts there are. You might want to get a kind of clue, like an idea as to where it might be. Like the 8 bits borrowed means that you're going to essentially have a Class C address. So each of your hosts, each of your networks can only hold 254 hosts. That kind of thing might be useful to remember when you take all of them. You add the amount of subnets that you can, and your number of hosts go down. So keeping track of the binary patterns is going to be useful. Just a little bit more about subnets that are just words to understand how they work. A subnet mask tells you how many bits you are going to borrow from your adjacent octets. So recognizing your subnet mask, if it is not 255.255.0.0, something like that, if it is a different number, then you know you're going to be borrowing some bits. So a full octet for a Class C IP address is going to have a mask of 255.255.0, which means we're not borrowing any from the adjacent octets. That will give us 254 hosts. How do I get 254 possible hosts? Well, 255 is 1111. Okay, so 255 for the third position is going to give us, 255 for whatever your remaining, how many do you have left? From that position, 255, we're going to take our 0 and subtract 2 from 255, and we'll get 255. 0 to 255 has a possibility of 256 nodes. 0 based means that there's one more than it looks like. If you were starting from 1, if we were counting, remember counting numbers, 1, 2, 3, 4, 5 will give you 5. 0, 1, 2, 3, 4, 5 will give you 6. So recognizing that we're starting from base 0, 0 to 255 gives you 256 possible nodes. But the first and the last nodes are reserved, the 0 and the 255. So the one with all zeros and the ones with all ones with all ones. Those are both reserved. So we have to subtract off of those 2, and you will end up with 254 hosts. So a full octet of a Class C address is going to give you 254 hosts. First and last are reserved. You have 1 through 254 as your possible hosts. That will be whatever your network IP address or a subnet is. So I don't know what we're doing in Class C. So 198.56.202.1 up to 254. Those are your possible IP addresses. So your host address is going to be 1 through 254. If you borrowed 2 bits from your fourth octet, so you started with a base Class C, 255 across, and then your fourth octet, we borrowed 2 bits. So we're going to borrow 11000000, which is 192. Our new subnet mask is 255, 255, 255, 192. Okay, that's going to go across. 192 minus 255, so the other half, what is the host part, is going to be 00, because those are the 2 bits we borrowed, 111111, which comes out to be 63, 1 less than 64. So that'll be 63. 0 to 63 gives you 64 possible nodes. Take out the 2 reserved, and you will get 62 possible nodes. Figuring out how to get those possible nodes by taking your subnet mask, what are the bits that you borrowed, what is the remaining node address, and then figuring out how many possible nodes we had in there. First and last, 0 and 63 are going to be used for reserve, and our available hosts are going to be 1 through 62. In the book, it simply asks you to subtract 1 from the 63. I'm hesitant to do that. The reason I keep saying you're borrowing 2 is because that's important. The first is going to be assigned to the network itself, and the last is going to be a broadcast address. These are both important to recognize that your first is always going to be the 0 value in that host. And the last is always going to be a broadcast, so it's always reserved. So rather than teaching you subtract 1, I'd rather explain you're borrowing 2, or you're reserving 2, but you're 0 based. So that's why you start from 1, go to 62. You can't use 0 and you can't use 63. When you make your subnets, it's important to recognize whether you have a variable length or a fixed length subnet mask. The subnets in a variable length subnet mask can vary in size, which means I can make a subnet that has 126 nodes, and I can make a subnet that has 62 nodes, and they can be different in size. They're called variable length subnet masks, and we use the identifier called CIDR, Classless Inter-Domain Routing, to define the different subnets and how many nodes are available. When you get into subnetting your network, you may choose to say the administration only needs 128 or 126, or even just 100, needs 100 possible nodes. But the students needs 400 possible nodes. So I want to make 2 different subnets, one that only has 100-ish possible nodes and one that has 400 possible nodes, so that I can have those separated. You can do that with a variable length subnet mask by being able to make your subnet mask, one of them only has 128 nodes, 126, and the other one has 510. So 512 minus 2. If all of your subnets are the same length, if I want to break it up into individual subnets where they are all the same length, they are all 512 or 510, every one of them has to be 510, then that would be a fixed length subnet mask. The subnet masks all have the same length. All the subnets are equal in size. The example that I've given here out of the book, so you can follow along in the book, converts a single IP address into 2 new subnets. In this situation, we started with 202.130.46.125. That was our base IP address. We had 255.255.255.0 as our subnet mask, which means it was a base class C. It was just your standard class C IP address. Okay, we want to take that IP address and subnet it down into 2 fixed length IP addresses. So we are going to borrow 2 bits from our 4th octet. Why 2? Because 2 bits gives us 0, 1, 2, 3 as our possible patterns, but 0 and 3 are already used because those are the reserves. So we have 2 possible patterns inside. We only need 2. So we're going to do just borrowing 2 bits to give us, of those 4, 2 possible patterns for our valid subnets. In the cases of our valid subnets, we have 0, 1 and 1, 0. When we do 0, 1, 0, 0, 0, 0, we get 64. So the 0, 1, 0, 0, 0, 0, 0, 0, sorry, I had to put in 6 there, is 64. And the second subnet is 128. These are our 2 possible subnets, 1, 0 and 0, 1. So we've broken up our possible subnets into 0 to 64 and 65 to 128. Okay, so 64 and 128 are our 2 valid subnets. Now, this is where it might get a little confusing. The maximum number of hosts per subnet is going to be 62 because we've talked about that. Each of these has 64 spaces available. 0 to 64 minus the 0 minus the 64, and we're going to end up with, 0 to 63. And we're going to end up with 62 possible values in there. Okay, now let's look at the possible host ranges. Remember, our subnet is going to be 202.130.46 and 64, 202.130.46 and 128. These are where our subnets start. Our possible host range is 1 more than the 64.0. So we're going to start at 65. So 64 being the last octet, we have to go up 1 more because we have to, our subnet gives us the range of our network, and then we have to go up to 65. So we're going to start from 65, and we can only go up to 126. So 127 is broadcast, 128 is the new network. So we can only go up to 126. So you can see 126 minus 65 is going to give us that 62 possible options in our host range, which means if I were to assign something that was in that first subnet, the 64 subnet, I would give a subnet mask of 202.130.46.64, and my host range would be 65 through 126. Okay, so the IP address would be 202.130.46.65, 66, 67, 202.130.46, 126, and then that would get me through to the 62 possible. If I were in the second subnet, the 128, I can start at 129, can't start at 128, it's already used, and I can go up to 190. Can't use 191, that's broadcast. Can't use 192 because that would be the next number up. Okay. The more you do the labs on how to calculate these, the better it's going to be for you. You need to sit down with a piece of paper. You need to sit down and scribble this out until you feel comfortable understanding how those numbers manipulate. Some of the labs, or study guide questions 1 through 4, I think, are all about calculating what is my new subnet mask, what is my valid subnets, what is my IP address, what is my node addresses for my host range, what is the range of possible hosts that I can put in there. Really important to get that math manipulation down. There's a lot of different ways to calculate this other than the way in the book. We're going to talk about CIDR in a couple of slides, and that gives another way of looking at it. So I want you to be aware this is going to be very math intense. The basic advantages and disadvantages. Advantages of subnetting. Since hosts can be on separate networks, it's more secure. Faster access to your resources because you're on separate networks, so the only people hitting your resources are the ones on your own network, so we split people off. Because the broadcast packets are only forwarded within a single network, there's less traffic on the network as a whole, which makes the network faster. There's less collisions because there's less stuff going along. Each network is broken off. Breaking up or subnetting is a good thing, and it is really, really useful in a large network to subnet or break down your different network into subnets to be able to do this, to make your network faster, to make it more secure, so on and so forth. Literally, the disadvantage is it gets confusing. Wow, that's a shocker. I wasn't confused already. Yes, IP assignment can be really confusing when it comes to subnetting. If you do it wrong, bad things happen. So if you set up your IP addresses wrong and you set up your host range wrong, you could have collision simply by having the same IP address assigned to multiple places. That'll cause problems. You could put people in the wrong subnet. That could cause problems. If you mess up your IP address, if you don't set it up correctly, it can actually make your system much worse. So that's the disadvantage. If you get confused assigning the IP address, bad things happen. However, the more you understand how the IP addresses are assigned, the easier the visualization will be when you're breaking it down, understanding the reason we use these numbers the way we do. Okay, we're going to get off of the math for a second and start talking about words again, and then we'll go back to CIDR in a couple of slides. So, devices that work for segmenting your network. So we're going to break up your network into subnets. You can segment using different devices. So, bridges, hubs, and switches. We're going to get to routers on the next slide. A switch versus a hub. Why would we use a switch versus a hub? Okay, a hub is going to pass all of the frames to everybody in the hub. Hub doesn't filter. So if you have a hub with 10 devices attached, every one of those 10 devices is going to get the broadcast that comes across. Hubs will split the possible bandwidth evenly with each connection, which means if the hub is attached to the network and it is 100 megabit bandwidth, and there's 5 devices attached, each device gets 20 megabits. It splits them evenly, which means even though you have a 100 megabit connection, each device only gets 20 because it goes through a hub, and the hub splits them. A switch, on the other hand, limits traffic only to the destination MAC addresses. So it filters. Because it filters, there's less bandwidth because you're not broadcasting everything to everybody. You're only sending it to the right address. Switches share the bandwidth between all connections. So if you have a 100 megabit connection, you can use 100 megabits at any given point. If there's nobody else sending any traffic and only one node is attached or one device is attached and sending traffic, it can use all 100 megabits. So you don't have to worry about that being segmented into only 1/5 of the possible bandwidth. Everything gets to go through. Switches versus hubs. Switches versus bridges. Okay, bridges in general are not used as much anymore because we can use switches. Bridges and switches both filter, and they filter based on MAC addresses. So bridges based on MAC addresses, switches based on MAC addresses. But switches will build a switch port table where they read the source MAC address to figure out what the MAC address is of the device that's sending it and start building a table so they know which one is which allows it to forward intelligently. It doesn't take as much effort. Bridges go and look at a MAC address table and figure out where am I sending it. You don't have to do that if you've already internally built your switch port table. The switches are a little faster. The other thing about switches is that they have possible forwarding modes. You can choose to set up your switch to handle collisions better. So, of the different forwarding modes for a switch, the first one is a cut through. As soon as it gets there, it reads the address and it moves it on. Forwards it as soon as it's received. It just goes straight through. It's the fastest, but it doesn't do anything to help you if there's any corrupt frames or if there's any problems. Store and forward will read the entire contents, drop any corrupted frames, and then forward. So any frames that are corrupt, they will read through, find out if there's any corrupt frames. If it is, it just drops it and then forwards the rest of it across. So any corrupted frames immediately get dropped, which means they don't get sent, which means they don't clutter up the internet. Fragment free is what we call it when you look at the first 64 bytes and then forward it. The theory being, if you're going to have corrupt frames, you're going to have them in the first 64 bytes, or you're going to have at least one in the first 64 bytes, and you're going to know that the rest of them are corrupt as well. You don't have to read through everything. So fragment free takes a little less space to look at things. If it's a very long frame and you're looking through the whole thing, fragment free only looks through the first 64 bytes and then sends it on, whereas store and forward looks through the whole thing. And the last one is what we call adaptive cut through. Okay, what adaptive cut through does is it does a basic cut through, forwarding as soon as it's received, until a number of corrupt frames are found. So once it finds out, as it's forwarding it, it's looking for frames, but it's still continuing to forward it. As soon as it finds out that there are some corrupt frames, it switches to a store and forward. Store and forward, remember, is going to read everything, drop all the corrupt frames, and move on. At the point that the store and forward doesn't have the cutoff number of frames, it goes back to cut through. So essentially it's looking at it and it's going, okay, I'm going to start and say, if there are 10 corrupt frames, I'm going to switch. So I'm running through and I'm looking, and finally I hit 10 corrupt frames. So I'm like, okay, stop. There's something wrong with this section. I'm going to switch to store and forward, and I'm going to keep looking at it. And, oh God, there was a lot of corrupt frames in here. Okay. All right, now we're better. Things are getting better. Okay, now I only have 9 corrupt frames. Cool. I can switch back to cut through because now I think it's all good. So it does this switch back and forth based on whatever you define as what is the number of corrupt frames that you want to find, want to stop at. And you could set it to 100, and you could set it to 1,000, and you could set it to 2. Whatever you feel like doing when it comes to the adaptive cut through, it will go ahead and stop, switch over, and then switch back as necessary. The point of a router, which is also a network segmenting device because it will allow you to segment, is to route packets to their proper destination. The purpose of a router is to route. Understanding the route and routing, it will route packets. Routing is simply selecting the best path for that packet. When we do our router metric, it's a mechanism to measure the best route. When we figure out our route, we measure them at hops. Okay, so a hop is a measure of how many network devices that the packet must pass through. We can use trace route, to be able to display the hops. Okay. A router has more functionality options than a switch. So it gives you more options and more things to do when it comes to segmenting or segmenting, being able to break up your network into segments. If you have multiple routers, each of the routers can segment your data. Routers are a layer 3 device. They are based on IP address. They are not based on MAC address. If they were MAC address, they'd be a layer 2, like switches. Switches, hubs, bridges, layer 2. Routers, layer 3. So they're up one layer. They're on the IP address. They can choose to use either a static or a dynamic IP address table, which is fine. And if all the dynamic IP tables are the same, we are in a state of convergence. Okay, let me explain that one a little bit more. Convergence is where there are multiple routers. So I have router A, B, and C. And all three of the routers are dynamically building their IP address table, which means each different router is figuring out what IP addresses are going to which devices, and they're building a table, kind of like our ARP table, to be able to build a table to be able to say, this IP address goes with this MAC address, this IP address goes with this MAC address, so I know where to send things and I can move things along with IP addresses. Remember, routers are IP based. So they can build their IP address table. You can manually go in and set the IP table. So you can say, this IP address goes with this one, this IP address goes with this is how this needs to be, and you can manually do it. But most routers are going to dynamically do that. As packets come in and get transferred through them, they will build their IP address table dynamically as things are going on the fly. If we have 3 routers in the office and each one of them is building them, they may not all start at the same table. However, at some point through traffic moving around, all 3 routers should have the same IP address data, because eventually they will all consist of the same information. When they all have the same data, we call that convergence. All 3 of them link the same IP addresses to the same MAC addresses, and they keep them all straight. So recognizing IP addresses in your static IP table or your dynamic IP table, when your dynamic IP tables are the same among all of your routers, we're in a state of convergence. That's a good state. And then just remember, a hop is that measure of how many network devices that the packet must go through. We looked at this when we were looking at trace routes, being able to say, you start from here and how many different routes did we go through to get to the end and back. Our router protocols. Yes, your router is going to use its own versions of protocols. And this gets really confusing. I recommend looking at this chart in the book, trying to understand which ones are which. Some of the questions, both in the homework, in the quiz, are going to ask you specific information about your router protocols. The Network Plus test, again, is going to bring up, if you're using this router protocol, what's going on type situation. Okay. First off, the 2 different types of protocols. We have our interior and exterior gateway protocols, and we have our link state and distance vector protocols. Start with the first 2. Our IGP, interior gateway protocol. IGP is for autonomous networks in a single domain. EGP, exterior, is between autonomous networks. So within the single network, or between 2 different networks is the difference between interior and exterior gateway protocol. So within my personal network, my singular autonomous network in a single domain, or between multiple autonomous networks. That's interior and exterior. Exterior between multiple, interior to stay inside. Our link state protocol. It does its own calculations and it doesn't really share its routing table, but it does transfer information about the individual connections. So link state protocols will keep things kind of personal. They do their own calculations, but they will transfer some information about how things are connected and how things are moved around. Our distance vector protocol shares its routing table. It sends that to other routers and lets them know this is what my routing table looks like. When you do that, eventually all the routers will be in a state of convergence because they'll all be sharing the same data. Every time you update your data, are you sending it off to all the other routers for the routers to understand? Okay, those are the basic types. Now let's look at the actual protocol names. So starting from the top, we have our exterior gateway protocol. EGP, as you notice, has an X in the EGP column. So row and column are both the same, and that might confuse you. Remember, EGP just means that it handles exchanges between different autonomous networks. BGP is Border Gateway Protocol, and it kind of replaced basic EGP. So Border Gateway Protocol contains lots of different route entries, like 90,000, and it gets actually assigned an IP address by IANA, and it's used as an autonomous system number, which it embeds into packets. When it embeds these into packets, it allows that to be shared as things go along. So remember, we're talking to outside networks. We're talking to other places, and we want to store that. So the BGP is the newer, updated version of EGP. It's the better version, and it exchanges its routing information with different networks. They both do. BGP being Border Gateway Protocol, and EGP just being exterior. Okay. Those two are a little different than the rest of them. All of the rest of them are internet gateway protocols. Internet, no, should be interior. I have to fix the slide. That's funny. Interior gateway protocols. These work inside of a single domain. So all of these work inside of a single domain. So we're going to start from the bottom and work our way up. That's actually how it is in the book, so it might help a little bit if you're following along in the book. RIP is Router Information Protocol, and it's the first one that we used. It was the original, one of the older protocols. And its purpose is to maintain a database of information about the network and then share it. That's what it does. It stores that information and shares it across. RIP2 also exists in that section. So the thing with RIP, though, is it can only support a minimum of 15 hops. Never occurred to them when they started this concept that we would have more than 15 hops, but obviously it does. So our next level of RIP is RIP Next Generation. Yes, just like Star Trek. So the Next Generation, NG, is the IP6 version of RIP. So we're going to do RIP, but we're going to do IP6 version of it. It's going to allow IP6 to actually handle its authentication, so it doesn't have to authenticate on its own, and it can handle much more than 15 hops. I think it's 255 hops that RIP Next Gen can hold. So those are RIP ones. Continuing to go up, we have 3 that are link state and 2 that are distance vector. So we're going to talk about the link state ones first. In our link state protocols, we have OSPF, which is Open Shortest Path First. Open Shortest Path First. It only exchanges information that has been recently changed in its table. So it detects network failures and then determines the best path after figuring out where the failures are. OSPF, Open Shortest Path First, is looking for a path, the shortest path, and it goes down that route. The next one up is the ISIS, which is the intermediate system to intermediate system, as opposed to ISIS. We don't talk about that. So the ISIS, intermediate system to intermediate system, is similar, but what it does is it actually defines a router type. Okay, we've talked about a ton of types and levels, and these can get very, very confusing. So your router type for an ISIS routing protocol gives you either a type 1 or a type 2. If you are a type 1, you are inside the network, and if you are if you're a level 1, you are inside the network, and if you're a level 2, you are outside the network. If the router is level 1, it can communicate with either 1 or 2. So it can either stay inside or it can go outside. But you can define your router to be a level 2 and only talk to other level 2 routers. This is a way of setting, this is my router that's assigned to go outside of my network. All the rest of my routers, they all stay inside. They can go outside, but they all stay inside. Nobody else can talk to them. They just talk to the internal people. When somebody from the outside wants to talk, they have to talk to a level 2 router, so they go to that one that is defined as the outside router. So that's how the ISIS, intermediate system to intermediate system, works. When we continue to move up, we get the IGRP and the EIGRP. Both of these are proprietary. They're both owned by Cisco. So Cisco built these. The regular IGRP is similar to the RIP, except instead of that 15, it does the 255. That's where I was going with that one. So it does the 255 and uses metrics based on bandwidth, latency, routing traffic, readability. These things all go into that IGRP protocol, which is a Cisco specific protocol. It's called distance vector because it's designed to share its routing tables with other routers. So that's the difference in IGRP. Of course, they couldn't stop there, so they created EIGRP, which is the enhanced interior gateway routing protocol. The enhanced version, this is the better one. What it does is it guarantees what they call loop-free operation. They make sure that there's no loops going on in your network, in your routing, so you don't waste time there. They advertise it as a link state protocol and a distance vector protocol. So they claim it's both because of the way that it's designed. It does share its routing table information, but it only shares some information across. And it's kind of this nice hybrid to prevent loops. So these are your different router protocols and the different ways that they're used. Now that we've introduced you to switches, let's introduce you to broadcast domains. So when we have a series of switches that create a certain broadcast domain where things are getting broadcast around, these are devices that are not connected by a router. So they're connected by multiple switches, multiple switches in a single broadcast domain, and we can use those. If you want to connect multiple VLANs or virtual LANs in with a router, you can do that as well. So if you look at this at the bottom, the smaller image, we have created broadcast domains, the top being 2 switches and the bottom being a 3rd switch with a router in the middle. 2 of the switches are attached to each other, so they are a broadcast domain. Inside of that broadcast domain, the switch can separate out virtual LANs. Virtual LAN up at the top with the first 2 on the left-hand side, then the bottom 2, then the top left, or the top right, and bottom right. So we've made 4 virtual LANs. Those 4 virtual LANs are controlled by those 2 switches. At the bottom, we have a 3rd switch with its virtual LAN hanging out down there. We have a router hanging out in the middle that is going to connect switch 2 to switch 3. When it does this, it allows the VLAN that's in the bottom right-hand corner with switch 2 to be in a grouping in a virtual or in a broadcast domain with switch 3. We can talk to those 2 people. So we can connect those. There are 5 virtual LANs that we have built here, recognizing even though there's 3 switches, each switch can break up into multiple virtual LANs. When you are in a broadcast domain, you forward all broadcast to all devices in your broadcast domain. That's the purpose of a broadcast domain. So being able to break those up into multiple broadcast domains can be useful. But if you want to do that between 2 switches, you have to add a router in the middle. The key difference between routers and switches. Routers are layer 3. They can create and separate networks. Switches are a single network. You cannot build a switch that is going to separate you into a different network. You have to be in the same network. You can subnet, you can build virtual LANs, but you cannot create an entirely new network with a switch. Switches just allow you to build internal virtual LANs, but they're not full-on networks. Routers can make full-on networks. They can do that because they're at a layer 3. A little bit more about virtual LANs before we go on to CIDR. We can have either a static or a dynamic virtual LAN. With a static virtual LAN, the physical ports are manually assigned to your VLAN. Manually. So we're going to say VLAN A, and we're going to put ports A, B, and C, 1, 2, and 3, into VLAN A. So we're manually setting it. Dynamic VLANs can be done by software, and a lot of times you're going to be using software because you're not going to be walking over to the switch and setting it manually. You're going to be using a piece of software to do it if you're using Cisco or if you're using something along those lines. So static versus dynamic. Dynamic just means the software does it and it figures it out, whereas static, you're manually setting it up. There is a concept called trunking. Trunking is where you connect multiple VLANs together with a single network line that we call the trunk. So the point of this is that a lot of data is going to go across there. So it's a larger line or a larger cable. You might be using fiber in this situation to be able to connect the different switches. You can do that with a trunk line. So VLAN trunking is connecting the LANs together on a single network line. And you can see in the image here where the trunk is. It's a single line that connects the switch to the router, and it's a single line that connects the switch to another switch. You would have a specific port assigned for the trunk port, so it understands its trunk. Again, two different types of protocols, always new protocols. Two protocols that you're going to be doing with trunking. The VTP, Virtual Trunking Protocol, is a Cisco protocol. Cisco protocol reconfigures the multiple switches over the network, so you figure one switch and all the others are automatically done for you. That's intentional. Cisco made this so that it was easier. If you don't use Cisco, then you will probably be using Spanning Tree Protocol, which is STP. Do not get this mixed up with Shielded Twisted Pair. I know they're the same acronym and it sucks, but it's the way acronyms work. The Spanning Tree Protocol actually uses an algorithm that we call Spanning Tree to figure out IP addresses to bridges and switches and ports. So it is designed to prevent what we call broadcast storms. If you mess up your bridges or switches and things are not set up correctly, STP should be able to go in and manage your network for you. So the Spanning Tree Protocol is going to be a level 2 protocol. It is done at the bridge and switch level, not at the router level. And it's designed to prevent broadcast storms if things are a problem. The switches can be connected to each other through routers in STP. In VTP, Virtual Trunking Protocol, you can connect them directly. Switches can be done correctly. So we talk about how switches need to be connected through routers, but VTP will allow you to do that with multiple switches. I've been alluding to CIDR for the entire lecture, so let me finally tell you what it is. CIDR notation is Classless Inter-Domain Routing, CIDR. And CIDR, CIDR, is a specific notation with a slash that tells you how many bits are used for the network. Back to our subnetting conversation at the beginning of the chapter. When we do our subnet, how many of your bits are being used for the network? Remember, there are 8 bits available at each octet. So a basic class A subnet mask, 255.0.0.0, is going to be a /8 because there's 8 bits used for the network. If you have a basic class B, you're going to have 16 bits, 255.255.0.0. Class C is 24 bits. Okay. Now, let's say we did a classless and we did a 255.255.255.192. So it's class C with 2 borrowed bits. The 2 borrowed bits adds to the 24 to make it a /26. We have a class B with 3 borrowed bits. I'm going to do 255.255.224, 0, and I'm going to 16 plus 3, or a total of 19. Okay, you're going to see on the next page the actual table of CIDR. But the way to remember how to calculate if you are given the CIDR, if you are given the subnet mask. Okay, if I'm given the subnet mask, like we just did for our classless mask in class B. Actually, this is a little different. So 255.255.240, 0. All right, we need to figure out how many bits are in 240. So we are going to look at our 128, 64, 32, 16, 8, 4, 2, 1, and figure out how many bits were necessary to get up to 240. If you want, you can always subtract this from 255 and get how many bits weren't included. In this case, it's the same number of bits either direction. So 128 plus 64 plus 32 plus 16 equals 240. So we know that that is 4 bits. 8 plus 8 plus 4 is a total of 20. So we know that 255.255.240, 0 has a CIDR of 20. If you want to do it the other direction where you subtract 240 from 255 to give yourself 15, how many bits do I need to get to 15? Well, I need an 8 plus a 4 plus a 2 plus a 1, which is also 4 bits. Subtract from 8 and you will get 4 bits. If you are given the CIDR and you need to figure out what the subnet mask is, again, this is part of your homework. You need to count how many whole 8 bits are there. So 255, 255, X, and 0. So in this case, we're going to have, for the CIDR of 22. 8 plus 8 is 16. One more 8 would be 24, and we can't go that far. So we know it's 16 plus 6. I need to figure out how many bits, or what number 6 bits is going to be. So 8 plus 6 is going to give me my 22. So I know my subnet mask is 255, something, and 0. That something is where you put in the number that comes out with 6 bits. Look at your 6 bits. 11111100. 128, 64, 32, 16, 8, 4. Or you can look at the other 2 bits, 0 and 1, or 1 and 2. 1 and 2 is 3. Take 255 and subtract 3, and you will get 252. So 252 is where that third position is going to be, that third octet. So 255, 255, 252, 0 is our subnet mask when our CIDR is 22. This slide will show you what your subnet mask is going to be, how many networks, and what class, and how many possible hosts for all 1 through 32 CIDRs. So 32 CIDRs and 31 CIDRs don't work because there's no nodes there. There's no possible node specific option in there. The smallest you can go is down to 30. So 30 is a 252, which gives you a total of 2 hosts, 64 networks. So your different subnet masks, networks, class, number of hosts. Yes, you could memorize this table. However, I highly recommend learning to calculate the CIDR rather than having to rely on your memory to memorize the table. The table is hard. There's a lot of information in here. And being able to break down your CIDR into my subnet mask by calculating it. So if I have a 12, well, 12 is 8 plus 4. 4 is 240. So I know it's going to be, so 4 bits, 11110000. So I know it's going to be 8, 255 plus 4, 240 plus 0 plus 0. That's easier for me, I would think, than memorizing this table, which is painful. So you can see it breaks it down into class A, Bs, and Cs, and then C subnets. These numbers should start to feel familiar. Maybe not the 2 billion number of hosts in a CIDR length of 1, but most of these numbers that you're getting into here, your 128, 64, 32, 16, 8, 4, 2, 1, those should feel familiar. And then maybe some of the other numbers that you're getting into with your base 2. So being able to reference your CIDR table, being able to calculate your CIDR is really, really important. One last little thing before we get to our homework is link aggregation. When you have 2 network cables or more paralleled with the intention of increasing bandwidth, you can take your server and have 2 different network adapters with 2 cables attached with 2 ports. You can have twice as much bandwidth. We call it link aggregation. The important thing about link aggregation is that you configure the ends before you actually connect the switches together. Otherwise, you could end up with a loop, and you don't want to end up with a loop. So make sure that you set up the ends of your link aggregation before you connect the different switches so that it can create this increased bandwidth and provide some extra redundancy in case one line goes down, the other one's available. All right. Subnetting, lots and lots and lots of math. And I know some of you may not be really strong on math. Some of you are probably really strong on math. Either way, I recommend doing the review questions because they're useful as always. In the study guide, 1 through 4 are going to ask you to manually start creating your subnets. So you're going to be taking some subnet information and you're going to be figuring out what is the subnet, what is the possible host addresses that are available. I highly, highly recommend you do this by hand. Because on the test, if you're taking the Network Plus test, you're not going to be able to have a calculator. You're not going to be able to have an online source to be able to find your subnetting. Yes, I know they're out there. I highly recommend you do this by hand because all you're getting on the Network Plus test, you don't even get a piece of paper. You get a little screen that you can type numbers into, but you don't even get a piece of paper to scribble on. So I recommend learning how to do all of these rather than using any type of a calculator. So 1 through 15 in the study guide. Then we get into the labs. So the first one is a binary conversion. There is in your Microsoft Windows a calculator. I'm pretty sure Mac has one too. Linux probably has one. One of the options in the calculator is binary. You can choose the binary option of the calculator type. It might be under programmer, it might be under scientific, but there's a binary option in there. So you can learn how to do binary conversions. Again, I recommend manually doing the binary conversions and then checking them with the calculator. But the point is for you to start being able to see some binary conversions. Lab 53 is a submess calculator. Okay, so Lab 53 uses something called SolarWinds. which is an application that you can get online that will be able to create your subnets. I want you to do it because I want you to know it's out there, but I still want you to practice manually when you do this. You can also use this to check your manual calculations and make sure that you're doing things right. Lab 54 is checking IPv4 subnets to build subnets. I actually recommend Packet Tracer for this, even if you have the ability to do this on your home computer. Packet Tracer will get you comfortable with the simulated environment to be able to build your subnets and do subnet masking. So that's labs 52, 53, and 54. Make sure you fill out the review questions and submit. StudyMate's available if you need it, and don't forget to take the quiz. Thank you for watching this video on subnetting, Chapter 11. Please come back next time for Chapter 12, and we'll continue with alternate versions of transmission. Have a great day.